Thank you very much for giving me an opportunity to talk this great workshop. My name is Yoshihiro Hirohashi, working in Denso Corporation, where we are developing components for intelligent camera systems for vehicle safety. This is a joint work with Okatani Laboratory in Tohoku University and my colleagues. Today, I will talk about our work with this title. First of all, please let me explain the background of this work. The surrounding monitoring cameras, or SMCs, equipped with a vehicle usually support the human drivers by displaying the view around the vehicle. In this example, we can perceive the sitting person here. However, how about the case in the right pane? In general, SMCs are weak in objects on the lens, such as raindrops, because they don't have a mechanism like a wiper. Can you see the sitting person behind the raindrop here? I think the answer is no. Then, is it possible to see the things occluded? In this work, we restore the degraded images by utilizing an image restoration method. There are many studies of image restoration to improve the quality of degraded images. In general, the strategies for image restoration are divided into two categories in terms of input to the algorithm. One is single image approaches, and the another one is multiple image approaches. We think that the single image approaches don't match our application because predicting what is occluded using a single image is difficult even for the human, if the occlusion area is large as shown here. On the other hand, we think multiple image approaches match our application, because previously observed things can be great hint for the restoration. Our method is based on recently proposed real-time video-inpainting method by Murase, and the restoration results are shown here. In general, video-inpainting method require mask to specify the restoration area. In this work, we assume that the mask is given in advance. As a result, we can see that sitting person is restored compared to the original image. This is another scene of the restoration result. In this study, we modified the existing work by Murase to improve the restoration quality. As we can see here, the quality of restoration is improved. In order to explain our method, we first review how the baseline method works. The method requires an input image and mask denoted as I1 and H1. At the first time step, the output image I1 hat is just masked image. At the second time step, the input image I2 and masked image H2 are provided. Then, the baseline method computes optical flow fields denoted by W. A problem is that the optical flow field in masked region is not well defined. The baseline method extends a CNN-based optical flow estimator to be able to estimate the optical flows for both masked and observed regions simultaneously. After optical flow field is estimated, we can geometrically copy the pixel values from the current image I2 for the unmasked region or previous frame result I1 hat for the masked region. This post-processing operation is denoted as warp and copy-paste module. Taking these operations repeatedly, we can also obtain restoration results for the following frames. So, the baseline method consists of two key components, optical flow estimator and the warp and copy-paste post-processing module. On the basis of this principle, in this study, we modified the post-processing module, denoted warp and copy-paste module, for improving the sharpness. In this slide, we explain how we improve the sharpness issue. Here, we describe the post-processing dynamics using one-dimensional signals for simplicity. The left pane shows the ground truth signal values. The horizontal and vertical axes indicate temporal and spatial axes, respectively. At the first time step, we have these monotonic pixel values. At the second time step, the signal is shifted 0.5 pixels, and the corresponding optical flows can be obtained as the blue arrows. We assume that accurate optical flows are available for the explanation. In the same way, we assume that the pixel values and optical flows are provided for the other time steps. We assume that the mask region is defined as a gray box. The post-processing of the baseline method is described in the center pane. We have already pixel values in unmasked region and optical flows for the all region. In the first time step, the pixel values are initialized to 0. In the following time step, the pixel values are computed from the values in previous frame and optical flows. However, we notice that there is a difference between original pixel values and the restored pixel values. In the case of the annotated pixel having 20, the computed value is weighted average of 0 and 30 and 25 and 20. We think these weighted average operations on many pixels act as a kind of low-pass filter, and thus the resultant images tend to be blurry. The proposed method avoids this problem. We assume the same setting of the baseline method. For the first two time steps, the pixel values in the mask region are not completed because the optical flow does not completely reach the visible pixel. At the third time step, we compute traced flow, denoted by the pink arrows here, by connecting existing optical flows to temporally map beyond the consecutive frames. When a traced flow reaches out the mask region, then the pixel completion is performed. By doing this, we can avoid the weighted average operation on many pixels, and thus we can obtain the images having sharpness. In this slide, we show several restoration results before and after the modification. All videos are cropped to focus the restored region. As we can see, the image restoration quality of sharpness is improved compared to the baseline method. This is the conclusion slide of our presentation. For visibility degradation issue due to the objects on the lens such as raindrops, we utilize the real-time video-inpainting method. In this work, we modified the existing video-inpainting method to improve the sharpness of the restoration image. In the future, we will tackle automatic mask estimation and validation in further realistic environment, including road reflection due to rain. Thank you very much for your attention.